What if the universe you see around you, the stars, the galaxies, the endless void of space, is only half the story? What if right now, in this very moment, another reality is pressing against our own, invisible and undetectable, yet impossibly close? Scientists have spent decades chasing shadows in particle accelerators and telescopes, and what they have found is starting to suggest something extraordinary. There may be another world, another version of existence itself, that has been touching ours since the beginning of time. If you enjoy exploring the deepest mysteries of the cosmos with us, please take a moment to like this video and subscribe to the channel. Your support helps us continue bringing you these peaceful journeys through the universe. So what exactly do physicists mean when they talk about another reality? Are we speaking of parallel universes like those in science fiction movies, where another version of you might be living a completely different life? Or is this something stranger, something that defies even our most creative imaginations? The truth, as it turns out, is far more fascinating than any story ever written. And to understand it, we need to start at the very foundation of reality itself, in the strange and beautiful world of quantum mechanics. Imagine for a moment that you are standing in a dark room. In your hand, you hold a single flashlight. When you turn it on, a beam of light cuts through the darkness, illuminating everything in its path. This seems simple enough. Light travels from the flashlight to whatever it touches, bouncing off surfaces and entering your eyes so you can see. But here is where things get strange. If you could zoom in on that beam of light, far beyond what any microscope could show you, you would discover that light is not a continuous stream at all. It is made up of tiny packets of energy called photons, and these photons behave in ways that challenge everything we thought we knew about the universe. When scientists first began studying the behavior of photons in the early 20th century, they encountered something deeply puzzling. In certain experiments, photons acted like particles, tiny bullets of light that traveled in straight lines and bounced off surfaces. But in other experiments, the same photons acted like waves, spreading out and interfering with themselves in patterns that only waves could create. This was not a matter of different types of photons or different conditions. The same photon could behave as a particle or a wave depending on how you chose to observe it. This discovery shook the foundations of physics. How could something be two different things at once? How could the act of observation itself change the nature of reality? These questions led to one of the most profound ideas in all of science, an idea that would eventually open the door to understanding how another reality might be intersecting with our own. The answer came from a physicist named Erwin Schrödinger, who developed a mathematical equation that described the behavior of quantum particles like photons and electrons. Schrödinger's equation did not describe a particle as a solid object in a specific location. Instead, it describes something called a wave function, a mathematical representation of all the possible states a particle could be in at any given moment. According to this equation, a photon is not just in one place or traveling in one direction. It exists in a kind of cloud of possibilities, spread out across space, until the moment you measure it. Only then does it seem to collapse into a single definite state. But what happens to all those other possibilities? When you measure a photon and find it in one particular location, what happens to all the other places it could have been? This is where the story gets truly remarkable, and where the idea of another reality first begins to emerge. In 1957, a young physicist named Hugh Everett proposed a radical answer to this question. Everett suggested that when you measure a quantum particle, the wave function does not actually collapse at all. Instead, the universe itself splits into multiple branches, with each possible outcome occurring in its own separate reality. In one branch of the universe, the photon is here. In another branch, the photon is there. Both outcomes are equally real, but they exist in different versions of reality that can no longer interact with each other. This idea became known as the many worlds interpretation of quantum mechanics, and it suggests something breathtaking in its implications. If Everett was right, then every quantum event that has ever occurred, every particle that has ever faced a choice between different possible states, has caused the universe to branch into multiple copies of itself. The number of parallel realities created by this process would be beyond comprehension, a number so vast that no human mind could ever grasp it. But here is the crucial question that scientists have been wrestling with ever since. If these other realities exist, are they truly separate from our own? Or is there some subtle connection between them? Some way in which they might still influence each other across the boundaries of existence itself? For decades, most physicists assumed that if parallel realities existed, they would be completely isolated from one another. The math seemed to suggest that once the universe branched, the different versions would diverge forever, never to meet again. But recent theoretical work has begun to challenge this assumption, and what researchers are finding is startling. There may be conditions under which different branches of reality can interact with each other, moments when the walls between worlds become thin enough for something to leak through. To understand how this might work, we need to dive deeper into the mathematics of quantum mechanics, into a phenomenon known as quantum interference. When two waves meet each other, they can combine in different ways. If the peaks of both waves line up, they amplify each other, creating a larger wave. If a peak meets a trough, they cancel each other out, creating a region of stillness. This is called interference, and it is one of the most fundamental behaviors of waves in nature. Here is the remarkable thing. Even single quantum particles can interfere with themselves. When a photon passes through two slits in a barrier, it does not simply go through one slit or the other. It somehow passes through both slits simultaneously, and the two paths interfere with each other on the other side, creating a pattern of light and dark bands. This interference pattern is proof that the photon existed in multiple states at once, taking both paths through the barrier as a wave before being detected as a particle. But what if the interference is not just between different paths through space? What if quantum particles can also interfere with versions of themselves from other branches of reality? This is the revolutionary idea that some physicists are now exploring, and it could explain phenomena that have puzzled scientists for years. Consider the strange behavior of quantum tunneling. In the classical world, if you throw a ball at a wall, it will bounce back every time, assuming the wall is solid enough. The ball does not have enough energy to pass through the barrier, so it simply reflects. But in the quantum world, particles can sometimes pass through barriers that should be impossible to penetrate. An electron approaching a solid wall will, on rare occasions, simply appear on the other side, as if the wall did not exist. This phenomenon is called quantum tunneling, and it is essential to many processes in nature, including the nuclear fusion that powers the sun. The standard explanation for quantum tunneling involves the wave function of the particle spreading through the barrier, allowing a small probability of the particle appearing on the other side. But some researchers have proposed an alternative interpretation. What if tunneling occurs because the particle is interacting with versions of itself from other branches of reality? What if the electron that appears on the far side of the wall has, in some sense, borrowed energy or momentum from its counterparts in parallel worlds? This idea might sound fantastical, but it is grounded in the mathematics of quantum mechanics, in a theory known as many interacting worlds, proposed by physicists Howard Wiseman and Michael Hall in 2014. Quantum phenomena arise precisely because parallel realities do interact with each other. In this model, there is no wave function at all. Instead, reality consists of many different worlds, each containing particles in slightly different positions. These worlds push against each other like crowds of people in a dense space, and this pushing creates the strange quantum effects we observe. The implications of this theory are profound. If many worlds are constantly interacting, then the boundary between our reality and its neighbors is not a solid wall at all. It is more like a membrane, flexible and permeable, allowing subtle influences to pass back and forth. The quantum strangeness we observe in our laboratories might be evidence of this interaction, fingerprints left by other versions of reality pressing against our own. But quantum mechanics is not the only place where scientists have found hints of other realities. When we turn our telescopes to the sky and look at the largest structures in the universe, we find patterns that are difficult to explain without invoking something beyond our observable cosmos. And this is where the story takes an even more dramatic turn. The universe we can see, the galaxies and stars and clusters of matter that fill our night sky, represents only a tiny fraction of what might exist. Light travels at a finite speed, and the universe is only about 13.8 billion years old. This means we can only see objects whose light has had time to reach us since the beginning of time. Beyond this cosmic horizon lies an unknown expanse, potentially infinite in extent, filled with matter and energy we will never be able to observe directly. Cosmologists have long wondered what lies beyond this horizon. Is the universe essentially the same out there as it is here, with more galaxies and more stars stretching forever into the darkness? Or could there be something fundamentally different, other regions of space with different physical laws or different configurations of matter? Some theories suggest that our observable universe is just one bubble in an infinite ocean of cosmic foam, surrounded by other bubbles with their own unique properties. This brings us to one of the most spectacular ideas in modern cosmology, the theory of eternal inflation. According to this theory, the Big Bang was not a unique event that created all of existence. Instead, it was just one local occurrence in a much larger process of cosmic expansion that has been going on forever and will continue forever. Different regions of space stop inflating at different times, creating separate bubble universes, each with its own Big Bang and its own history of cosmic evolution. If eternal inflation is correct, then our universe is just one of countless bubbles floating in an infinite void, surrounded by other universes that might be very different from our own. The physical constants that govern our reality, things like the strength of gravity or the mass of the electron, might have different values in these neighboring bubbles. Some of these universes might be completely inhospitable to life, while others might contain forms of existence we cannot even imagine. But here is where the idea of intersecting realities becomes relevant. In the eternal inflation scenario, bubble universes are not necessarily isolated from each other. Under certain conditions, two bubbles can collide, their boundaries merging and separating in violent cosmic events. When this happens, energy and information can flow from one universe into another, leaving marks on the fabric of space itself. Cosmologists have been searching for evidence of such collisions in the cosmic microwave background, the faint glow of radiation left over from the early universe. This radiation fills all of space and carries within it a record of conditions shortly after the Big Bang. Any collision with another bubble universe would leave a distinctive bruise on this cosmic canvas, a circular region where the temperature or density of the radiation differs from its surroundings. Several research groups have claimed to find such anomalies in the cosmic microwave background. The data from satellites like WMAP and Planck have revealed unexpected cold, spots and asymmetries that are difficult to explain with standard cosmology alone. While none of these observations provide definitive proof of a collision with another universe, they are tantalizing hints that something unusual may have happened in the early cosmos, something that might point to the existence of other realities beyond our own. But there is another way to think about intersecting realities, one that comes from the cutting edge of theoretical physics and the attempt to unify all the forces of nature into a single framework. This approach takes us into the realm of string theory and the concept of extra dimensions, where the idea of multiple realities takes on an entirely different meaning. In our everyday experience, we perceive 3 dimensions of space and 1 dimension of time. We can move forward and backward, left and right, up and down, and we experience the passage of time from past to future. But according to string theory, the universe might have many more dimensions than this, dimensions so small or so different from the ones we know that we cannot perceive them directly. String theory proposes that the fundamental building blocks of matter are not point particles, but tiny vibrating strings of energy. These strings are unimaginably small, far smaller than anything we could ever hope to observe. The different vibration patterns of these strings give rise to different particles, explaining why the universe contains such a variety of matter and forces. But for the mathematics of string theory to work, the strings must vibrate in more than 3 dimensions of space. Depending on the version of the theory, there could be 10 or 11 dimensions in total. Where are these extra dimensions? If they exist, why do we not experience them? One possibility is that the extra dimensions are curled up so small that they are invisible to us. Imagine an ant walking along a garden hose. The ant perceives 2 dimensions of motion, along the length of the hose and around its circumference. But to us, standing far away, the hose looks like a one-dimensional line. The circular dimension is still there, but it is too small to see from a distance. In the same way, the extra dimensions of string theory might be curled up at scales far smaller than any particle, hidden from our direct perception. But there is another possibility, one that has profound implications for the idea of intersecting realities. What if some of the extra dimensions are not small at all? What if they are vast, potentially infinite in extent, but we cannot perceive them because we are stuck to a particular region of higher dimensional space? This is the idea behind brane cosmology, one of the most exciting developments in theoretical physics over the past few decades. In this picture, our entire visible universe, everything from the smallest atom to the largest galaxy cluster, exists on a 3-dimensional surface embedded in a higher dimensional space. This surface is called a brane, short for membrane, and it represents the totality of our observable reality. But here is the stunning implication. If our universe is a brane floating in higher dimensional space, then there might be other branes out there, other 3-dimensional universes existing parallel to our own. These parallel branes could be incredibly close to us in the extra dimensions, perhaps only a fraction of a millimeter away, but we would be completely unaware of their presence because we cannot perceive the extra dimensions that separate us. Imagine 2 sheets of paper lying nearly on top of each other. Each sheet represents a universe filled with matter and energy, with its own stars and galaxies and perhaps its own forms of life. The 2 sheets are separated by only a tiny gap in the 3rd dimension, but beings living on either sheet would have no way of detecting the other. They would perceive only the two dimensions of their own sheet, completely unaware that another world was floating just beside them. This is the picture that emerges from brane cosmology, and it raises a fascinating question. If parallel branes exist, can they interact with each other? Can anything pass between them, bridging the gap between separate realities? According to the theory, most things cannot cross between branes. The particles that make up ordinary matter, like electrons and quarks, are confined to our brain, stuck like specks of dust on the surface of the paper. They cannot wander off into the higher dimensional bulk because the physics does not allow it. But there is one thing that might be able to escape, one type of particle that could potentially move through the extra dimensions and make contact with other branes. That particle is the graviton, the hypothetical carrier of the gravitational force. In string theory, gravity is different from the other forces of nature. While electromagnetism and the nuclear forces are confined to our brain, gravity can leak out into the extra dimensions, spreading its influence into regions that matter cannot reach. This is why gravity appears so weak compared to the other forces. Its strength is diluted across multiple dimensions, leaving only a fraction of its power to act within our own reality. If gravity can leak out of our brain, then it can also leak in. The gravitational pull of matter on a neighboring brane could reach across the extra dimensions and affect objects in our own universe. This interaction would be subtle, perhaps too subtle to detect with our current instruments, but it would represent a genuine connection between separate realities, a bridge across the void that divides different worlds. Some physicists have proposed that this interaction might explain one of the biggest mysteries in modern cosmology, the nature of dark matter. Dark matter is the name given to the invisible substance that seems to make up most of the mass in the universe. We cannot see dark matter directly because it does not emit or absorb light. But we know it is there because of its gravitational effects on visible matter. Galaxies rotate faster than they should based on the mass we can see, and light from distant objects bends as it passes through space, warped by the gravity of something invisible. What if dark matter is not a new type of particle at all? What if it is ordinary matter, just like the matter we know, but located on a parallel brane? The gravity of this matter would leak across the extra dimensions and affect our universe, pulling on our galaxies and bending our light. But we would never be able to see it directly because it exists in a separate reality. In this picture, dark matter is simply matter in another world, a world that is touching ours through the invisible hand of gravity. This idea is still speculative, and there are many alternative explanations for dark matter that do not require parallel universes. But the possibility remains intriguing, a hint that the dark corners of our cosmos might be illuminated by light from other realities. The concept of brane cosmology also offers a dramatic explanation for the origin of our universe itself. In the traditional picture of the Big Bang, the universe began from a state of infinite density and temperature, a singularity where the laws of physics as we know them break down. What caused this singularity? What existed before the Big Bang? These questions have puzzled cosmologists for generations, because the singularity seems to represent a boundary beyond which we cannot probe. But in brane cosmology, the Big Bang might not have been the beginning of everything. Instead, it might have been the result of a collision between two branes, a cosmic crash that released enormous amounts of energy and gave birth to our universe. Picture two parallel sheets drifting through the higher dimensional bulk, gradually moving closer and closer together. When they finally collide, the energy of the impact creates a tremendous explosion, heating both branes to incredible temperatures and filling them with particles and radiation. This is the Big Bang, not a creation from nothing, but a transformation caused by the interaction between two pre-existing realities. This model, known as the ekpyrotic scenario, suggests that our universe has gone through multiple cycles of creation and destruction. The two branes collide, separate, and eventually collide again, each impact generating a new Big Bang and a new epoch of cosmic evolution. Our current universe is just one chapter in an eternal story, a single collision in an endless series of cosmic encounters. If this is true, then another reality has not just been intersecting with ours. It has been responsible for our very existence. The world we inhabit, everything we see and touch and experience, might owe its being to a moment of contact between parallel universes, a brief touch that ignited the fires of creation. But how can we test these extraordinary ideas? How can we gather evidence for something that exists beyond the boundaries of our observable universe? This is where the story enters the realm of cutting-edge experiments and observations, where scientists are pushing the limits of technology in search of answers. One of the most promising approaches involves the search for gravitational waves, ripples in the fabric of space itself caused by violent cosmic events. When massive objects like black holes collide, they send out waves that travel across the universe at the speed of light, stretching and compressing space as they pass. In 2015, scientists at the LIGO Observatory made the first direct detection of gravitational waves, opening a new window on the cosmos and earning a Nobel Prize for their achievement. Gravitational waves are interesting in the context of other realities because, unlike light or matter, they might carry information from beyond our brain. If gravity can leak between dimensions, then gravitational waves generated on a parallel brane could potentially reach our detectors, appearing as mysterious signals with no visible source. Such signals would be extraordinarily difficult to identify, lost among the noise of ordinary cosmic events, but the possibility remains that we might someday detect the gravitational whisper of another universe touching our own. Another experimental approach involves the study of quantum gravity effects at the smallest scales. According to some theories, the fabric of space-time is not smooth and continuous, but has a foamy, granular structure at distances far smaller than an atom. This quantum foam might contain tiny wormholes or fluctuations that briefly connect different regions of space, including potentially regions in other branes or other branches of the quantum multiverse. Detecting these quantum gravity effects is incredibly challenging because they occur at scales far beyond the reach of any particle accelerator we can build. But some physicists have proposed that these effects might leave subtle imprints on the behavior of particles or the propagation of light over vast cosmic distances. By studying gamma-ray bursts and other energetic phenomena from the far reaches of the universe, we might be able to catch glimpses of the granular structure of space-time and learn whether it connects us to something beyond. There is also the intriguing possibility of creating or detecting extra dimensions in laboratory experiments. If the extra dimensions predicted by string theory are larger than previously thought, then particle colliders like the Large Hadron Collider might be able to probe them directly. When particles collide at extremely high energies, some of that energy might escape into the extra dimensions, appearing as missing energy in the detector. This would be a sign that something is leaking out of our reality, disappearing into regions of space we cannot perceive. So far, the Large Hadron Collider has not found definitive evidence for extra dimensions, but the search continues. future colliders with even higher energies might succeed where current machines have not, pushing back the frontiers of knowledge and perhaps revealing the hidden geometry of space itself. Let us pause for a moment and consider what all of this means. The theories we have explored, from the many worlds interpretation to brane cosmology to eternal inflation, all suggest that our universe is not alone. Whether through quantum branching, collision with other bubbles, or proximity to parallel branes, our reality appears to be connected to something larger, something that exists beyond the boundaries of what we can see and touch. But there is a question we have not yet addressed, a question that strikes at the very heart of what it means to exist. If other realities are out there, intersecting with our own, what does that mean for us? What does it mean for the significance of our lives, our choices, our place in the cosmos? In the many worlds picture, every decision you make, every quantum event in your brain, causes the universe to split into multiple branches. There is a version of you who took the job you turned down, a version who married the person you never asked out, a version who stayed home on the day you decided to travel. Every path not taken is taken somewhere, in some branch of the quantum tree, leading to a version of reality where your life unfolded differently. Some people find this idea disturbing. If every possibility is realized somewhere, then do our choices really matter? If there is a version of us making every possible decision, then what makes this version, the one we experience, special or significant? But perhaps we can look at this differently. The many worlds. Interpretation does not say that your choices do not matter. It says that your choices determine which branch of reality you continue to experience. The version of you reading these words right now is a specific, unique individual, shaped by a particular sequence of decisions and events. The other versions are not you. They are other people, other minds, living other lives in other branches of the cosmic tree. Your choices matter because they define who you are, distinguishing you from all the other versions that might have been. There is also something strangely comforting about the idea that all possibilities are realized. It means that nothing is ever truly lost. The paths not taken are still there, existing in their own branches of reality, full of their own joys and sorrows and discoveries. The universe, in all its branching complexity, contains every story that could ever be told, every life that could ever be lived. In a sense, this is the ultimate expression of cosmic completeness, a reality so rich and full that nothing is left out. Of course, we cannot know for certain whether the many worlds interpretation is correct. It is one of several competing interpretations of quantum mechanics, and the debate among physicists continues. But the fact that such ideas are taken seriously by leading scientists shows how far our understanding of reality has come. We live in an age when the concept of multiple realities is not just science fiction, but a legitimate topic of scientific inquiry. Now, let us turn to the cosmological picture and consider what it might mean if our universe has collided with others in the past or might collide with them in the future. The eternal inflation scenario suggests that our bubble universe is just one of infinitely many, floating in an eternal sea of expanding space. Some of these bubbles might be very different from our own, with different physical laws and different structures. Others might be nearly identical, copies of our universe in every meaningful way. If our bubble has collided with another in the past, that collision might have left marks on our cosmic microwave background, the ancient light that fills all of space. Some researchers believe they have already found hints of such marks, anomalies in the data that do not fit neatly into standard cosmological models. While these findings are controversial and far from conclusive, they suggest that the evidence for other realities might already be written in the sky, waiting for us to learn how to read it. And what if a collision is coming in the future? What would happen if another bubble universe were to crash into ours, merging two separate realities into one? The consequences would be beyond catastrophic. The physics of the collision region would be utterly foreign to anything we know, potentially destroying matter as we understand it and replacing it with something else entirely. Such an event would spell the end of our reality, at least in the region of space where the collision occurs. But we should not lose sleep over this possibility. The distances involved in the multiverse are unimaginably vast, and even if other bubbles exist, the chances of a collision reaching us in any reasonable time frame are essentially zero. The universe is old, but it is not old enough for trouble to have traveled from distant bubble boundaries to our corner of the cosmos. We are safe, at least for now, cocooned in our little pocket of reality, while the larger structure of the multiverse goes about its eternal business. The brane cosmology picture offers yet another perspective on the meaning of intersecting realities. If our universe is a three-dimensional surface floating in a higher dimensional space, then we are like the characters in a story, unaware of the pages that lie above and below us. Other branes might contain other stories, other characters, other plots unfolding in parallel to our own. And just as gravity might leak between branes, influencing events across the dimensional gap, perhaps other things might leak as well. Information, patterns, echoes of what happens in one reality might somehow imprint themselves on another. Some researchers have speculated about the possibility of communication between branes. If gravity can travel through the extra dimensions, then perhaps carefully modulated gravitational signals could carry information from one brane to another. This is highly speculative, and the technical challenges would be enormous, but it raises the tantalizing possibility that intelligent beings on a parallel brane might someday reach out to us, or that we might reach out to them. The universe might be filled with messages we have not yet learned to hear, signals from other realities calling across the void. Let us now consider some of the more exotic possibilities that emerge when we take the idea of intersecting reality seriously. If different versions of reality can influence each other, what are the limits of this influence? Could it be possible, under the right circumstances, for matter or energy to actually pass between realities? Could there be doorways, however small or rare, that allow objects to move from one branch of the quantum tree to another? Some theoretical physicists have explored the concept of traversable wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe or even different universes altogether. Einstein's equations allow for the existence of wormholes, but they typically require exotic forms of matter with negative energy to keep them open. Whether such matter exists or could ever be created is unknown, but the mathematical possibility remains. If wormholes between realities could exist, even briefly, they might explain some of the strange phenomena that people have reported throughout history. Unexplained appearances and disappearances, objects that seem to come from nowhere, the persistent feeling that reality is not quite as solid as it seems. Of course, we should be careful here. Most such reports have mundane explanations, and the human mind is remarkably good at seeing patterns and mysteries where none exist. But in a universe where other realities might be touching our own, we should perhaps keep our minds open to possibilities that seem strange. There is also the question of consciousness and how it relates to the structure of reality. Some interpretations of quantum mechanics give a special role to the observer, suggesting that the act of measurement or observation is what causes the wave function to appear to collapse into a definite state. This has led some thinkers to speculate about the relationship between mind and multiverse, wondering whether consciousness might somehow span multiple branches of reality or have access to information from beyond our immediate experience. These ideas venture into philosophical territory that goes beyond what physics can currently test. But they remind us that the question of other realities is not just about particles and waves and extra dimensions. It is also about the nature of experience itself, about what it means to be a conscious being in a universe that might be far vaster and stranger than we ever imagined. As we drift deeper into this exploration, let us consider the emotional and spiritual implications of living in a multiverse. For many people, the vastness of even our single universe is already overwhelming. The distances between stars are so great that light, the fastest thing in existence, takes years or centuries or millennia to cross them. Galaxies are separated by millions of light years, and the observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. Against this backdrop of cosmic immensity, it is easy to feel small and insignificant, a tiny speck of consciousness lost in an indifferent void. The idea of multiple realities takes this feeling to a whole new level. If there are infinitely many branches of the quantum tree, infinitely many bubble universes, infinitely many parallel branes, then our little planet Earth is not just a tiny part of a vast universe. It is a tiny part of one tiny part of an infinite collection of realities, each as vast and complex as our own. The numbers involved are so large that they cease to have meaning. Infinity times infinity. Worlds without end. Amen. And yet, perhaps this is exactly the point. The universe, in all its unimaginable vastness, does not have to make us feel small. Instead, it can remind us of how extraordinary it is that we exist at all. Out of all the possible configurations of matter and energy, out of all the different ways the cosmos could have evolved, here we are. Conscious beings, aware of our own existence, able to contemplate the stars and wonder about the nature of reality. This is not insignificance. This is a kind of miracle. The multiverse, if it exists, is not something to fear or feel diminished by. It is something to marvel at, to explore with curiosity and wonder. Every branch of the quantum tree, every bubble universe, every parallel brane contains its own stories, its own mysteries, its own opportunities for beauty and meaning. We happen to be telling our story in this particular branch, this particular bubble, this particular brane. And that is enough. That is more than enough. Let us now return to the science and consider some specific predictions and observations that might help us determine whether other realities truly intersect with our own. As we have discussed, the cosmic microwave background offers one potential source of evidence. This ancient light, released when the universe was only about 400,000 years old, carries within it a record of conditions in the early cosmos. Any unusual events, like a collision with another bubble universe, would leave their mark on this radiation. The most famous anomaly in the cosmic microwave background is the cold spot, a region in the southern sky where the temperature is significantly lower than average. This spot is about 5 degrees across, making it one of the largest structures ever observed in the universe. Various explanations have been proposed for the cold spot, including the presence of a giant cosmic void, a region of space with fewer galaxies than usual. But some cosmologists have suggested that it might be evidence of a collision with another universe, a bruise left behind when two bubble realities briefly touched. The evidence for this interpretation is far from conclusive. The cold spot could have many explanations, and the statistical significance of the anomaly is still debated. But the fact that such explanations are even considered shows how seriously physicists take the possibility of other realities. The cold spot might be nothing more than a random fluctuation in the ancient light of the cosmos. Or it might be a window into something far more profound, a glimpse of the multiverse beyond our own. Another potential source of evidence comes from the study of gravitational waves. As we mentioned earlier, these ripples in space-time were first detected in 2015, and since then, dozens of events have been observed. Most of these events have clear explanations, typically the merger of two black holes or two neutron stars. But as our detectors become more sensitive, we might someday observe signals that do not fit the expected patterns, waves that seem to come from nowhere, or have properties that cannot be explained by any known astrophysical process. Such anomalous signals could potentially be evidence of gravitational waves leaking in from another brane or another branch of reality. The chances of detecting such signals are slim, and distinguishing them from ordinary cosmic noise would be extraordinarily difficult. But the search is worth pursuing. Every time we push the boundaries of observation, we risk discovering something that overturns everything we thought we knew. The search for extra dimensions at particle colliders offers another experimental avenue. The Large Hadron Collider, the most powerful particle accelerator ever built, smashes protons together at energies approaching 7 trillion electron volts. At these energies, physicists can probe distances smaller than a billionth of a meter, searching for signs of new physics beyond the standard model. One of the things physicists look for is missing energy. When particles collide, energy is conserved, so the total energy before and after the collision should be the same. If some energy seems to disappear, it might mean that something has escaped into regions of space that our detectors cannot observe. In particular, if gravitons are produced in the collision and escape into extra dimensions, they would carry energy away from our brane, appearing as missing energy in the data. So far, no definitive evidence for extra dimensions has been found at the Large Hadron Collider. The data are consistent with the standard model of particle physics, which does not include extra dimensions or graviton production. But the search continues, and future colliders with even higher energies might succeed where current experiments have not. The discovery of extra dimensions would be one of the most important scientific breakthroughs in history, confirming that our reality is just one part of a higher dimensional whole. There are also proposed experiments that would specifically search for evidence of interacting parallel worlds. The many interacting worlds theory makes certain predictions about the behavior of quantum systems that differ from the standard quantum mechanics. These differences are subtle, but in principle they could be detected with sufficiently precise measurements. If the theory is correct and parallel worlds do influence each other, we might be able to see the fingerprints of this interaction in laboratory experiments. Such experiments would need to be extremely sensitive, able to detect deviations from standard quantum predictions at levels beyond what is currently achievable. But technology continues to advance, and what seems impossible today might become routine tomorrow. The history of science is full of discoveries that seemed beyond reach, until suddenly they were not. As we consider all these possibilities, it is worth reflecting on what we are really searching for. The question of other realities is ultimately a question about the nature of existence itself. What does it mean for something to be real? What is the relationship between our experiences and the underlying structure of the cosmos? These are questions that philosophers have grappled with for millennia, and now they are becoming questions that scientists can address with observation and experiment. The answer might be that reality is far stranger than we ever imagined. It might be that our universe is one island in an infinite archipelago, one story in an endless library, one dream in a mind beyond comprehension. Or it might be that we are alone after all, a single reality hanging in an empty void, unique and precious and utterly alone. Either way, the search is worth pursuing. The quest to understand our place in the cosmos is one of the noblest endeavors of the human spirit, and it does not matter whether the answer brings us company or confirms our solitude. What matters is that we ask the question, that we look up at the stars and wonder, that we push against the boundaries of the known in search of something more. Let us continue our journey now and explore some of the deeper theoretical frameworks that scientists have developed to understand the structure of reality. These frameworks are mathematical and abstract, but they contain ideas of breathtaking beauty and elegance. In their equations and diagrams, physicists have glimpsed possibilities that challenge our most basic intuitions about space, time, and existence. One of the most important theoretical tools for understanding intersecting realities is the concept of the wave function of the universe. In ordinary quantum mechanics, the wave function describes a single particle or a small system of particles. It encodes all the probabilities for where the particle might be found, what momentum it might have, and so on. When you make a measurement, the wave function appears to collapse, selecting one outcome from among all the possibilities. But what happens when you apply this concept to the entire universe? The universe, after all, is just a very large quantum system, made up of countless particles all obeying the laws of quantum mechanics. In principle, there should be a wave function that describes the entire cosmos, encoding all the possibilities for how the universe might be configured. This idea was first proposed by physicists John Wheeler and Bryce DeWitt in the 1960s. The Wheeler-DeWitt equation, as it came to be known, is a mathematical description of the quantum state of the universe. It treats the entire cosmos as a single quantum object, subject to the same rules of probability and superposition that govern atoms and electrons. The implications of this equation are profound. If the universe has a wave function, then it exists in a superposition of all possible states until somehow measured or collapsed. But who or what could measure the entire universe? There is no outside observer, no laboratory beyond the cosmos that could perform such a measurement. The universe, it seems, must somehow collapse itself, selecting its own reality from among infinite possibilities. This is where the many worlds interpretation becomes compelling. If there is no external observer to collapse the wave function of the universe, then perhaps it never collapses at all. Instead, the universe simply exists in all its possible states simultaneously, with different branches of reality corresponding to different terms in the wave function. Every possibility is realized, and the appearance of a single definite reality is just an illusion created by our limited perspective within one branch. The Wheeler-DeWitt equation has another remarkable property. When physicists tried to solve it, they discovered that the equation has no explicit dependence on time. The wave function of the universe is static, unchanging, eternal. This seems to contradict our everyday experience, where time is constantly flowing and events unfold in a definite sequence. How can the fundamental equation of the universe be timeless when our experience of reality is so deeply temporal? The answer may lie in the concept of emergent time. According to some interpretations, time is not a fundamental feature of reality, but emerges from the relationships between different parts of the wave function. When we, as observers embedded within the universe, experience the passage of time, we are actually experiencing a particular sequence of correlations within the eternal, timeless wave function. Different observers in different branches of reality might experience different flows of time, depending on how they are correlated with the rest of the cosmos. This idea has profound implications for the nature of intersecting realities. If time is not fundamental but emergent, then the concept of simultaneity between different branches of reality becomes meaningless. One branch might be in what we would call the past, another in the future, and a third in a completely different sequence of events that has no correspondence to our timeline at all. The multiverse in this picture is not just spatially vast but temporally complex, containing realities at every stage of cosmic evolution, all existing together in the eternal present of the wave function. Let us delve deeper into string theory and explore how it illuminates the structure of the multiverse. As we mentioned earlier, string theory proposes that the fundamental constituents of matter are not point particles, but tiny, vibrating strings. The different vibration patterns of these strings give rise to different particles, much like the different notes produced by a vibrating guitar string. For the mathematics of string theory to be consistent, the strings must vibrate in extra dimensions beyond the 3 spatial dimensions we perceive. The most popular version of string theory requires 10 dimensions in total, 9 of space and 1 of time. But there are other versions, and they are all connected by a web of mathematical relationships known as dualities. These dualities are among the most remarkable discoveries in theoretical physics. They show that different string theories, which appear to be completely different on the surface, are actually just different descriptions of the same underlying reality. A theory with small extra dimensions can be equivalent to a theory with large extra dimensions. A theory with strong interactions can be equivalent to a theory with weak interactions. These equivalences hint at a deeper unity underlying all the different versions of string theory, a master theory that encompasses them all. This master theory is sometimes called M theory, though no one knows exactly what M stands for. Mother theory, master theory, mystery theory, all have been suggested. What we do know is that M theory exists in 11 dimensions rather than 10, and it includes not just strings, but also higher dimensional objects called branes. These branes can have any number of dimensions, from 0-dimensional points to 9-dimensional objects that fill nearly all of space. The existence of branes in ours, M theory provides the foundation for brane cosmology. Our universe, in this picture, is a 3-dimensional brane floating in the 11-dimensional bulk of M theory. Other branes float nearby, each potentially hosting its own universe with its own physical laws. The interactions between these branes, mediated by gravity and other forces that can travel through the bulk, might account for some of the mysterious phenomena we observe in our cosmos. One of the most intriguing possibilities raised by M theory is the concept of the landscape. The equations of string theory have not just one solution, but an enormous number of solutions, each corresponding to a different possible configuration of the extra dimensions. When the extra dimensions are curled up, the precise shape of this curling determines the physical laws that govern the resulting 4-dimensional universe. Different shapes give rise to different particle masses, different force strengths, different values of the fundamental constants. The number of possible shapes is astronomically large, estimated to be around 10 to the power of 500 or more. This number is so vast that it defies comprehension. To put it in perspective, the number of atoms in the observable universe is only about 10 to the power of 80. The landscape of string theory contains more possible universes than there are atoms in everything we can see. If all these possibilities are actually realized, if there is a universe corresponding to each shape in the landscape, then the multiverse is unimaginably diverse. Some universes would have physics similar to our own, with recognizable particles and forces. Others would be utterly alien, with different numbers of dimensions, different types of matter, different flows of time. The variety is limitless, and our particular universe, with its specific laws and constants, is just one point in this vast landscape. This idea has been both celebrated and criticized by physicists. Some see it as a natural extension of our understanding, a way to explain why the universe has the particular properties it does. If all possibilities are realized, then we should not be surprised to find ourselves in a universe compatible with the existence of conscious observers, because only such universes can contain anyone to ask the question. This reasoning is known as the anthropic principle, and it has a long history in cosmology and philosophy. Others see the landscape as a problem, a sign that string theory makes no definite predictions and cannot be tested. If anything is possible somewhere in the multiverse, then nothing is predicted for our particular universe. This critique is serious, and it has motivated physicists to search for ways to make more specific predictions from string theory, ways to constrain the possibilities and identify what should or should not be observed. Let us now explore another fascinating aspect of intersecting realities, the role of information and its relationship to the structure of the multiverse. In recent decades, physicists have come to appreciate that information is not just an abstract concept, but a fundamental feature of physical reality. The laws of physics conserve information, and the structure of the universe can be understood in terms of information processing and storage. This perspective has led to some remarkable insights about the nature of reality. One of the most surprising is the holographic principle, which suggests that all the information contained in a three-dimensional region of space can be encoded on the two-dimensional boundary of that region. This is like saying that the entire contents of a room, every object and every particle, can be completely described by a picture painted on the walls. The holographic principle emerged from the study of black holes, where it was discovered that the maximum amount of information that can fit in a region of space is proportional to the area of the boundary, not the volume. This counterintuitive result suggests that we might be living in a kind of hologram, where the three-dimensional world we perceive is actually a projection from a two-dimensional surface far away. How does this relate to intersecting realities? If our universe is a hologram, then the information that defines our reality is encoded on a distant boundary. This boundary could, in principle, be shared with other regions of the bulk, creating connections between different holographic projections. Two universes that appear completely separate in the bulk might be linked through shared information on a common boundary, creating subtle correlations between events in different realities. The holographic principle also suggests that the ultimate nature of reality might be quite different from what we perceive. The familiar three-dimensional space in which we move and live might be an approximation, emerging from a more fundamental description in fewer dimensions. The intersections between realities might not occur in the way we naively imagine, as physical contacts in space, but as information exchanges across dimensional boundaries. Let us consider the concept of quantum entanglement and how it might relate to the multiverse. Entanglement is one of the most mysterious and fascinating phenomena in quantum mechanics. When two particles become entangled, they are linked in a way that persists regardless of the distance between them. A measurement on one particle instantly affects the other, even if they are on opposite sides of the universe. Einstein famously called this spooky action at a distance, and he found it deeply troubling. How could information travel faster than light? How could the universe know to correlate distant events instantaneously? The answer, according to modern physics, is that no information actually travels during entanglement. The correlations are built in from the start, encoded in the quantum state of the entangled system. But what if entanglement extends across different branches of reality? In the many worlds picture, every quantum measurement causes the universe to branch, with different outcomes realized in different branches. But the branches are not entirely independent. They are all part of the same wave function, connected through quantum correlations that persist even after the split. Some physicists have proposed that entanglement might provide a window into other branches of reality. By studying the correlations between entangled particles, we might be able to detect influences from other versions of the universe, subtle signs that our reality is interacting with its neighbors. This is highly speculative, but it shows how creative thinking can suggest new avenues for exploring the multiverse. There is also the intriguing connection between entanglement and the structure of space-time itself. In recent years, theoretical physicists have discovered that entanglement might be the glue that holds space together. According to this view, the geometry of space-time emerges from the quantum entanglement between different regions. Without entanglement, space would fall apart into disconnected pieces, losing its coherent structure. This idea has led to the slogan that entanglement equals space-time, or more precisely, that the geometry of space can be reconstructed from the pattern of entanglement in the underlying quantum system. If this is correct, then the connections between different realities might also be understood in terms of entanglement. Parallel universes that share entangled particles might be linked by threads of space-time, bridges of quantum correlation that span the dimensional gap. Let us now turn our attention to the philosophical implications of intersecting realities. The existence of other universes raises profound questions about the nature of existence, causation, and meaning. Philosophers have grappled with these questions for millennia, but the scientific discovery that other realities might actually exist gives them new urgency and relevance. One of the central questions is the problem of identity. If there are multiple versions of you in different branches of reality, which one is really you? Are they all you, each with an equal claim to your identity? Or are you specifically the version in this branch, with the others being separate individuals who merely resemble you? Different philosophers have given different answers to this question. Some argue for a branching identity, where a single person splits into multiple successors at each quantum event. On this view, you are not a unique individual, but a tree of related selves, spreading across the multiverse with each passing moment. Others argue that identity requires continuity, and that the versions in other branches, however similar, are distinct persons from the moment the split occurs. There is also the question of free will. If all possible choices are realized in some branch of reality, can any choice be truly free? When you decide to turn left rather than right, there is a version of you in another branch who turned right. Both outcomes were inevitable, given the structure of the wave function. Does this mean your choice was determined in advance, or does it mean that you genuinely chose, with the multiverse simply recording all possible choices? These questions have no easy answers, and reasonable people disagree about how to resolve them. but they remind us that the multiverse is not just a matter of physics and mathematics. It touches on the deepest questions of human existence. Questions about who we are, what we can control, and what our lives mean in the vast context of cosmic reality. Let us reflect now on the beauty and wonder of the universe we inhabit, whatever its ultimate structure might be. Whether we are one reality among many or the only reality that exists, we live in a cosmos of extraordinary beauty and complexity. Galaxies spiral through the void, stars ignite and die, planets form and occasionally give birth to life. The process that led from the Big Bang to conscious beings contemplating the stars is a story of incredible creativity and emergence. This story would be no less meaningful if it were repeated in countless other branches or bubbles or branes. Every version of the story would be precious, every instance of beauty and wonder worth celebrating. The multiverse, if it exists, is not a diminishment of our significance, but an amplification. It means that the creativity of the cosmos is not limited to one outcome, one path, one history. It means that all the stories that could be told are told, all the lives that could be lived are lived, all the beauty that could exist does exist. As we drift through these ideas, letting them wash over us like gentle waves, we can find peace in the uncertainty. We do not need to know the final answers to appreciate the questions. We do not need to see other realities to be inspired by the possibility that they exist. The search for understanding is itself a kind of gift, a journey through the landscape of ideas that enriches our experience of being alive. The night sky has always been a source of wonder for humanity. Our ancestors looked up at the same stars we see today, the same moon, the same wandering planets. They did not know what they were seeing, but they felt the pull of mystery, the sense that something vast and ancient was looking back at them. That sense of wonder has not diminished with scientific knowledge. If anything, it has grown deeper and richer as we have learned how much there is to discover. The possibility of other realities is part of this deepening wonder. It is a reminder that the universe contains more than we can see, more than we can measure, more than we can comprehend. Every step forward in understanding opens new vistas of mystery, new questions to pursue, new depths to explore. This is not a bug in the process of science, but a feature, a guarantee that our sense of wonder will never be exhausted. Let us continue now with our exploration and consider some specific scenarios that might arise if different realities are indeed intersecting with our own. These scenarios range from the subtle to the dramatic, from effects we might detect with sensitive instruments to events that would transform our understanding of existence itself. One of the most subtle effects of intersecting realities would be small deviations from the predictions of standard quantum mechanics. If the many interacting worlds theory is correct, and parallel realities do push against each other, then the behavior of quantum systems should differ slightly from what the standard equations predict. These deviations would be tiny, perhaps too small to detect with current technology, but they would provide direct evidence that other worlds are influencing our own. Imagine an experiment where single particles are sent through a maze of barriers and detectors. In standard quantum mechanics, the probability of the particle reaching each detector can be calculated precisely. But if parallel worlds are interacting, the probabilities might be slightly different, nudged by the presence of countless other versions of the particle in nearby branches of reality. Detecting these deviations would require extraordinarily precise measurements, but the payoff would be revolutionary. We would have proof that we are not alone, that our reality is just one thread in a vast tapestry of interconnected worlds. Another possible effect involves quantum interference patterns. As we discussed earlier, particles like photons can interfere with themselves when they pass through multiple paths simultaneously. The interference pattern depends on the relationship between the different paths, with constructive interference where the paths add together and destructive interference where they cancel out. If other realities are interacting with ours, the interference patterns might be affected by the presence of particles in other branches. The pattern we observe would not just be the result of interference between paths in our world, but would include contributions from paths in neighboring worlds as well. This could create subtle anomalies in the interference pattern, deviations from the standard predictions that would hint at the existence of the multiverse. Some physicists have proposed searching for such anomalies in precision experiments with atoms and molecules. Modern atomic clocks are so accurate that they can detect changes of 1 second over billions of years. Interferometers can measure distances to within a fraction of the width of an atom. These instruments might be sensitive enough to detect the subtle influences of other realities, if we know what to look for. Moving to larger scales, the intersection of realities might manifest as unexpected correlations in cosmological data. If our universe has been influenced by contact with other bubble universes or other branes, these influences might leave statistical signatures in the distribution of galaxies, the pattern of cosmic structure, or the properties of distant light sources. Consider the large-scale structure of the universe. Galaxies are not scattered randomly through space, but are organized into a cosmic web of filaments and voids. The distribution of matter in this web depends on the initial conditions in the early universe, seeded by tiny quantum fluctuations during inflation. If another universe has interacted with ours, it might have perturbed these initial conditions, creating anomalies in the cosmic web that differ from what standard cosmology predicts. Astronomers have indeed found several unexplained features in the large-scale structure of the universe. There are alignments and patterns that seem statistically unlikely, regions where the distribution of galaxies does not match expectations. While most of these anomalies probably have mundane explanations related to incomplete data or systematic errors, some might be genuine hints of something beyond our current understanding. The cosmic microwave background, that ancient glow from the early universe, offers perhaps the clearest window into possible interactions with other realities. We have already mentioned the cold spot, a mysterious region of lower temperature that some have attributed to a collision with another bubble universe. But there are other anomalies as well. One is the so-called axis of evil, an unexpected alignment in the pattern of temperature fluctuations in the cosmic microwave background. The fluctuations seem to be correlated with the plane of our solar system in a way that should not happen if the universe is isotropic, meaning the same in all directions. This alignment has puzzled cosmologists since it was first discovered, and no convincing explanation has emerged. Another anomaly is the hemispherical asymmetry, a difference in the statistical properties of the fluctuations between one half of the sky and the other. Again, standard cosmology predicts that the universe should be the same in all directions, but the data suggest otherwise. These asymmetries might be evidence of inhomogeneities in the early universe, perhaps caused by the influence of other realities during the inflationary period. Let us now imagine more dramatic scenarios, events that would unmistakably demonstrate the existence of other realities. While these scenarios are speculative, they are grounded in the theoretical frameworks we have discussed and illustrate the range of possibilities that physics allows. One such scenario involves the detection of gravitational waves from another universe. As we have seen, gravitational waves can, in principle, travel through the higher dimensional bulk of M-theory, leaking from one brane to another. If a catastrophic event occurred in a parallel universe, like the collision of two supermassive black holes, or the explosion of an unstable brane, the gravitational waves might reach our detectors as mysterious signals with no visible source. Current gravitational wave detectors, like LIGO and Virgo, are designed to detect waves from sources within our universe. They look for the characteristic chirp signature of merging black holes, the distinctive wobble of neutron star collisions. A signal from another universe would look different, perhaps lacking the expected waveform, or coming from a direction with no corresponding light source. Such a signal would be extraordinarily difficult to interpret, but it would open a window into realms beyond our own. Another scenario involves the direct observation of extra dimensions. According to some versions of string theory, the extra dimensions might be accessible at energies achievable in particle accelerators. If a collision at the Large Hadron Collider or a future collider created particles that disappeared into extra dimensions, we would have direct evidence that our reality is embedded in a larger dimensional space. Even more dramatic would be the creation of microscopic black holes in particle collisions. Some theories predict that black holes could form at energies much lower than previously thought, if extra dimensions allow gravity to become stronger at small scales. These black holes would evaporate almost instantly through Hawking radiation, producing a burst of particles that our detectors could observe. While this might sound dangerous, such microscopic black holes pose no threat. They would be far smaller than an atom and would vanish in a fraction of a second. Perhaps the most dramatic scenario of all would be actual contact between our brane and another. If two branes were drifting toward each other in the higher dimensional bulk, they might eventually touch, creating a region where the physics of both universes come into contact. What would happen in such a region is difficult to predict. The laws of nature might blend and merge in unpredictable ways. Matter from one brane might be able to interact with matter from the other. The very structure of space-time might become unstable. Such an event would be catastrophic on a cosmic scale, but it would also be the ultimate confirmation that other realities exist. If we could observe such a collision from a safe distance, we would witness the most extraordinary event in the history of the universe, the merger of two separate realities into something new. Of course, there is no evidence that such an event is imminent or even possible. The branes in M-theory might be separated by enormous distances in the extra dimensions, far beyond any possibility of collision. Or the forces between branes might be repulsive, pushing them apart and preventing contact. The mathematics allows for many possibilities, and without more data, we cannot know which scenario is correct. Let us step back now and consider the broader picture. We have explored many different theories and ideas, from quantum mechanics to string theory, from eternal inflation to the holographic principle. Each offers a different perspective on the possibility of other realities, and together they paint a picture of a cosmos far richer and more complex than we could have imagined a century ago. The common thread running through all these ideas is the notion that our observable universe may not be all there is. Whether through quantum branching, bubble nucleation, brane cosmology, or something else entirely, physics seems to point toward a reality that extends beyond the horizon of our perception. The multiverse, in one form or another, appears to be a natural consequence of our best theories about the fundamental nature of existence. But we should be careful not to overstate the case. The multiverse remains a hypothesis, not a proven fact. The evidence is suggestive, but not conclusive. Many of the theories that predict other realities are themselves not fully understood or tested. String theory, for all its mathematical beauty, has yet to make a single definite prediction that has been confirmed by experiment. The many worlds interpretation, while consistent with quantum mechanics, is not the only way to understand the quantum world. Science proceeds by making predictions and testing them against observations. For the multiverse, this is extremely difficult because, by definition, other universes are beyond our direct observation. We can look for indirect evidence, like anomalies in the cosmic microwave background or deviations from standard quantum predictions. But confirming the existence of other realities with the certainty we demand of scientific claims may be impossible. This does not mean the multiverse is not worth studying. Theoretical exploration is valuable even when direct experimental tests are not available. Understanding the implications of our theories, following the mathematics where it leads, can teach us important things about the structure of reality, even if some conclusions remain forever uncertain. And perhaps the test will come. Science has surprised us before, finding ways to observe phenomena that seemed forever hidden. A century ago, no one could have imagined detecting gravitational waves or the cosmic microwave background. Who knows what technologies and techniques future generations will develop? The multiverse might remain hidden, or it might eventually reveal itself in ways we cannot yet anticipate. Let us now take a deep breath and allow ourselves to simply wonder. Forget the mathematics and the experiments for a moment. Forget the debates between different interpretations and theories. Just consider the possibility, as a thought experiment, that you are living in a multiverse of unimaginable scale. Somewhere, in another branch of the quantum tree, there is a version of you who made different choices. Perhaps they pursued a different career, loved different people, lived in a different place. Their life has unfolded in ways you can only imagine, shaped by choices you considered but did not make. They are not you, not exactly, but they share your history up to the point of divergence. In some sense, they are the road not taken made real. Somewhere, in another bubble universe, the laws of physics are different. Perhaps the force of gravity is stronger, causing stars to burn brighter and die faster. Perhaps there are more dimensions of space, allowing forms of life and complexity we cannot conceive. Perhaps the very concept of life as we know it does not apply, and something entirely other has emerged from the quantum foam. Somewhere, on another brane floating in the 11-dimensional bulk, an entire universe exists parallel to our own. It might be similar to ours, with galaxies and stars and planets, or it might be utterly alien. Its inhabitants, if it has any, might be looking up at their own sky, wondering about the nature of reality, asking the same questions we ask. They would be separated from us by a distance in extra dimensions smaller than the width of an atom, yet utterly unreachable by any means we know. These are not just fantasies or stories. They are possibilities allowed by the mathematics of our best physical theories. They might be true, or they might not be. But the fact that they are possible, the fact that we can contemplate them seriously as scientists and not just as dreamers, is itself remarkable. The human mind has always reached for the infinite. Our religions speak of heavens and hells, of worlds beyond the material plane. Our myths tell of journeys to other realms, of heroes who crossed boundaries between different orders of existence. The multiverse, in some ways, is the scientific version of these ancient intuitions, a rigorous exploration of the possibility that reality extends far beyond what we can see and touch. But the multiverse differs from myth in one crucial way. It is constrained by evidence and mathematics, by the demand that our theories be consistent and predictive. The multiverse of physics is not a refuge for wishful thinking or magical belief. It is a consequence of taking our best theories seriously, following the equations where they lead, even when they lead to strange and uncomfortable places. And the multiverse, if it exists, is not a place of escape. We cannot travel to other branches of the quantum tree or visit other bubble universes. We are bound to this reality, this branch, this bubble. The other versions of us, if they exist, are as unreachable as the most distant galaxies, perhaps more so. The multiverse does not change our practical situation. It only changes our understanding of the context in which that situation exists. Let us return now to the science and consider what the future might hold for our understanding of intersecting realities. The coming decades will bring new telescopes, new particle accelerators, new gravitational wave detectors. Each of these instruments has the potential to reveal something unexpected, something that could shift our understanding of reality in profound ways. The James Webb Space Telescope, launched in 2021, is already transforming our view of the cosmos. Its infrared eyes can see further back in time than any previous instrument, observing galaxies as they were when the universe was young. While it was not designed to search for evidence of other universes, its data might contain surprises that we cannot anticipate. The universe has a way of revealing secrets we did not know we were looking for. Future particle colliders, if they are built, will probe energies far beyond what is currently achievable. The proposed future circular collider would be nearly 100 kilometers around, dwarfing the Large Hadron Collider. At such energies, physicists hope to discover new particles, new forces, perhaps evidence for supersymmetry or extra dimensions. Any of these discoveries could reshape our understanding of the fundamental structure of reality. The next generation of gravitational wave detectors will be even more sensitive than LIGO and Virgo. The Laser Interferometer Space Antenna, or LISA, will be a space-based detector capable of sensing gravitational waves from the most massive events in the cosmos. The Cosmic Explorer and Einstein Telescope are proposed ground-based detectors that could see 10 times further into the universe than current instruments. With these tools, we might detect signals that current detectors miss, perhaps including signals that hint at the existence of other realities. There are also more speculative proposals, experiments that might directly probe the intersection of different realities. Some researchers have suggested looking for quantum effects in large objects, searching for evidence that macroscopic systems can exist in superposition states, or that the boundaries of the quantum world extend further than we thought. Others have proposed experiments to test the holographic principle, looking for signatures of the two-dimensional origin of our three-dimensional world. Whatever happens, the search will continue. Humanity's curiosity about the nature of reality is inexhaustible. Every answer leads to new questions. Every discovery opens new mysteries. The multiverse, whether we confirm it or not, will remain a source of wonder and inspiration for generations to come. Let us now bring our journey full circle and return to the question with which we began. What does it mean if another reality has been intersecting ours since the beginning of time? What are the implications for our understanding of the cosmos and our place within it? The first implication is humility. We have always known that the universe is vast, but the multiverse takes this vastness to a new level. Our observable universe, with its hundreds of billions of galaxies, might be just one tiny patch in an infinite landscape of realities. our particular branch of the quantum tree, with its specific history and configuration, might be one among countless others. The cosmos, it seems, is even more magnificent than we dared to imagine. The second implication is connection. If other realities are touching ours, then we are not isolated. Even if we cannot communicate with other branches or other bubbles, we are part of a larger whole. The forces that shape our universe, the quantum fluctuations that seeded cosmic structure, the fundamental constants that allow us to exist, all are connected to something beyond. We are not alone in the deepest possible sense. We are part of a cosmic community, even if we never meet our neighbors. The third implication is wonder. The universe is endlessly fascinating, endlessly surprising. Every time we think we have understood its limits, we discover that there is more. The multiverse is the latest chapter in this ongoing story of discovery, a reminder that reality will always exceed our grasp. This is not a cause for despair, but for celebration. The universe rewards curiosity with endless revelations. As our journey through these ideas draws to a close, let us take a moment to appreciate the extraordinary time in which we live. We are the first generation to seriously contemplate the existence of other realities using the tools of science. Our ancestors could only dream of such questions. Future generations will know things we cannot imagine. But we are here now, at this pivotal moment, when the multiverse is transitioning from speculation to science. Whatever the ultimate truth about the multiverse turns out to be, the journey of discovery is valuable in itself. We learn not just about the universe, but about ourselves, about what it means to be curious beings in a cosmos that responds to our questions with ever deeper mysteries. The multiverse might be real, or it might be a beautiful mathematical possibility that nature chose not to realize. Either way, contemplating it enriches our understanding and expands our imagination. Let us explore further the idea of quantum decoherence and how it relates to the branching of realities. When we speak of the universe splitting into multiple branches at each quantum event, we might wonder why we do not experience this splitting directly. Why do we perceive a single, consistent reality rather than a blur of overlapping possibilities? The answer lies in a process called decoherence. When a quantum system interacts with its environment, the different possible states of the system become entangled with the states of the environment. This entanglement effectively destroys the interference between different possibilities, making the system behave as if it were in one definite state, rather than a superposition. Decoherence happens incredibly quickly for macroscopic objects. A grain of dust floating in the air interacts with countless air molecules and photons every second, becoming entangled with its environment so thoroughly that any quantum superposition is instantly destroyed. For all practical purposes, everyday objects have definite positions and velocities, even though at the quantum level they are subject to the same rules as individual particles. In the many worlds interpretation, decoherence explains why we perceive distinct branches of reality. When a quantum event occurs, the universe splits into branches corresponding to different outcomes. Decoherence ensures that these branches do not interfere with each other, so we experience only one branch at a time. The other branches are there, existing in the vast wave function of the universe, but they are invisible to us because the interference has been washed out. This picture has interesting implications for the intersection of realities. Even though different branches of the quantum tree cannot interfere with each other after decoherence has occurred, the underlying wave function still connects them. They are all part of the same mathematical structure, different terms in the same equation. In some sense, the branches never truly separate. They just become distinguishable, losing the ability to directly influence each other while remaining part of a unified whole. Some physicists have speculated about what might happen if decoherence could be reversed. If we could somehow undo the entanglement between a system and its environment, could we restore the interference between different branches? Could we access other versions of reality by peeling back the layers of environmental interaction? This is not currently possible and may never be possible. Decoherence involves an enormous number of degrees of freedom, and reversing it would require controlling the quantum state of every particle that has interacted with the system. Even for a single photon, this would mean tracking its interactions with atoms, molecules, and other photons throughout the universe. The practical obstacles are insurmountable, but the theoretical possibility remains intriguing. It suggests that the separation between branches of reality is not absolute, not a fundamental feature of the universe, but a consequence of the complexity of environmental interactions. In principle, all branches remain connected through the unified wave function, even if accessing those connections lies beyond our technological capabilities. Let us now consider the relationship between consciousness and the multiverse. This is a topic that has fascinated physicists, philosophers, and mystics alike, and it remains one of the most mysterious aspects of the question of other realities. Consciousness, whatever it is, seems to involve a unified experience of the world. We do not perceive all possible states of a quantum system simultaneously. We perceive one definite outcome at a time. This selectivity is part of what makes consciousness so puzzling in the context of quantum mechanics. If the wave function contains all possibilities, why does conscious experience single out just one? In the many worlds interpretation, the answer is that consciousness does not single out one possibility from the wave function. Instead, consciousness splits along with the universe, with each branch containing its own conscious observers experiencing that particular outcome. The unified experience of consciousness is an illusion, in the sense that there are multiple versions of each conscious being, each experiencing a different branch. But this raises deep questions about the nature of personal identity and the continuity of consciousness. When the universe branches, what happens to the unity of experience? Are the different versions of you really you? Or are they separate beings who happen to share your past? Philosophers have debated these questions extensively, and there is no consensus on the answers. Some thinkers have proposed that consciousness might play a more fundamental role in the structure of reality. In these views, the observer is not just a passive recipient of quantum outcomes, but an active participant in determining which outcomes become real. The act of observation on this view does not just reveal the state of the universe, but helps create it. These ideas are controversial and difficult to test, but they remind us that the question of other realities is not just about physics and mathematics. It is also about the nature of mind and its relationship to the physical world. Any complete understanding of the multiverse will need to account for the peculiar fact that conscious beings exist within it, wondering about its structure and their place in it. Let us explore the concept of cosmic inflation in more detail, as it is one of the most important foundations for the idea of multiple universe bubbles. Inflation is the theory that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. During this expansion, the universe grew from smaller than an atom to larger than a galaxy in less than a trillionth of a trillionth of a trillionth of a second. Inflation was originally proposed to solve several puzzles in cosmology. Why is the universe so flat, so close to the critical density that separates eternal expansion from eventual collapse? Why is the cosmic microwave background so uniform in temperature, even in regions that seem too far apart to have ever been in contact? Inflation answers these questions by proposing that the entire observable universe originated from a tiny patch of space, which was then stretched to cosmic scales by the exponential expansion. But inflation has another remarkable implication. The quantum fluctuations that occurred during the inflationary period were stretched to astronomical scales, becoming the seeds of all cosmic structure. These fluctuations explain why the universe is not perfectly uniform, why there are galaxies and clusters and voids. Without the quantum fluctuations of inflation, the universe would be a featureless soup of particles with no stars, no planets, no life. The connection to other realities comes from the nature of the inflationary process. According to many models, inflation is not a one-time event, but an eternal process. Different regions of space stop inflating at different times, each becoming a separate bubble universe with its own Big Bang. The inflationary background continues forever, spawning an infinite number of bubbles, each with potentially different physical properties. This eternal inflation creates a multiverse of staggering proportions. The number of bubble universes is not just large, but literally infinite. And within each bubble, quantum branching creates further multiplicity, with every quantum event splitting the bubble into multiple branches. The total number of realities, if we count both bubbles and branches, exceeds any finite quantity. The multiverse in this picture contains everything that is mathematically possible. Some cosmologists have embraced this picture as a natural consequence of our best theories. Others have criticized it as unfalsifiable speculation, a philosophical commitment masquerading as science. The debate continues, with both sides making important points about the nature of scientific knowledge and the limits of what we can know. Whatever one thinks about the multiverse, it is undeniable that inflation has been remarkably successful in explaining the observable universe. The predictions of inflation match the data from the cosmic microwave background with extraordinary precision. The theory is not a mere speculation, but a well-tested framework that has passed numerous empirical challenges. The question is whether the multiverse implication of inflation should be taken seriously, or whether it is an artifact of extrapolating the theory beyond its domain of validity. Perhaps inflation occurred, but stopped everywhere at some point, leaving only a single universe rather than an infinite collection. Or perhaps the inflationary model itself is incomplete and a more fundamental theory will modify or eliminate the multiverse prediction. Let us now consider the role of probability in a multiverse context. In ordinary physics, probability tells us how likely different outcomes are. If we flip a coin, there is a 50% chance of heads and 50% chance of tails. If we roll a die, there is a 1 in 6 chance of each number. These probabilities are based on our ignorance of the detailed state of the system and become precise predictions when we consider many trials. But in the multiverse, probability becomes more puzzling. If all possible outcomes actually occur in different branches or bubbles, what does it mean to say that some outcomes are more likely than others? Every outcome happens with certainty somewhere in the multiverse. There is no uncertainty at the fundamental level, only the appearance of uncertainty from within a particular branch. This is known as the measure problem, and it is one of the most difficult challenges facing multiverse theories. To make predictions, we need a way of counting or weighting the different branches or bubbles, deciding which ones are more common or more representative. But the multiverse is infinite, and comparing infinite quantities is notoriously tricky. Different ways of defining the measure give different predictions, and there is no obvious way to choose between them. Some physicists believe the measure problem can be solved, that there is a natural way of assigning probabilities in the multiverse that gives sensible predictions. Others see it as a fundamental obstacle, a sign that the multiverse concept is not well defined and may need to be abandoned or radically revised. Let us reflect on the anthropic principle and its role in multiverse reasoning. The anthropic principle observes that any universe in which we exist must have properties compatible with our existence. This seems almost tautological, yet it has surprising explanatory power in the context of the multiverse. Many of the fundamental constants of physics appear to be finely tuned for the existence of complex structures like atoms, molecules, stars, and life. If the strength of gravity were slightly different, stars would not form, or they would burn too quickly to allow the development of life. If the mass of the electron were slightly different, chemistry as we know it would be impossible. The list goes on, with many constants apparently needing to fall within narrow ranges for anything interesting to happen. In a single universe, this fine-tuning seems like an extraordinary coincidence, a puzzle crying out for explanation. But in the multiverse, it becomes less mysterious. If there are infinitely many universes with different values of the constants, then some will inevitably have the right values for life. We necessarily find ourselves in one of those, because only such universes contain observers to ask the question. This reasoning does not explain why the constants have the values they do. It only explains why we observe those values, by noting that we could not exist to observe anything else. Critics argue that this is not really an explanation, but an evasion, a way of giving up on the search for deeper reasons. Supporters counter that it is a legitimate application of probabilistic reasoning, no different from explaining why we find ourselves on a habitable planet rather than floating in empty space. The anthropic debate touches on deep questions about the nature of explanation in science. What counts as a satisfying answer to a why question? Must there always be a unique, necessary reason for things being the way they are? Or is it acceptable to say that things could have been otherwise, and we happen to find ourselves in one particular possibility out of many? These questions have no easy answers, and reasonable scientists disagree. But the anthropic principle, controversial as it is, has become an important part of the conversation about other realities. Whether we accept it or reject it, we must grapple with its implications for how we understand our place in the cosmos. Let us now turn to some of the more speculative ideas that have emerged from thinking about intersecting realities. These ideas push the boundaries of current physics and venture into territory that is not yet well understood. They are not established science, but creative explorations of what might be possible. One such idea involves the concept of cosmic natural selection. Proposed by physicist Lee Smolin, this theory suggests that black holes might give birth to new universes. When matter collapses to form a black hole, it might trigger a new Big Bang on the other side, creating a baby universe with slightly different physical constants than its parent. If this is true, then universes that produce more black holes will have more offspring, and their properties will come to dominate the multiverse through a kind of natural selection. Over cosmic time, the multiverse would evolve toward universes that are good at making black holes, just as biological evolution produces organisms that are good at reproducing. Interestingly, the conditions for producing many black holes seem to overlap with the conditions for producing life. Both require the formation of stars, which fuse light elements into heavier ones before sometimes collapsing into black holes. So cosmic natural selection might explain the fine-tuning of the constants, without appealing to the anthropic principle directly. This idea is speculative and difficult to test. We cannot observe the birth of new universes inside black holes or measure the properties of their descendants. But it illustrates the kind of creative thinking that the multiverse inspires, the way that contemplating other realities opens up new possibilities for understanding our own. Another speculative idea involves the simulation hypothesis, the possibility that our universe might be a computer simulation running on some higher level of reality. This idea has gained popular attention in recent years, though it has been discussed by philosophers for much longer. If our universe is a simulation, then the simulators, whoever they are, exist in a reality beyond our own. Their computers, using whatever physical laws govern their realm, are running the program that generates our experience of space, time, matter, and energy. Everything we see and touch, everything we are, would be patterns of information in their computational substrate. The simulation hypothesis is related to the multiverse in interesting ways. If simulations are possible, then they might be common, with advanced civilizations throughout the multiverse running countless simulations of various kinds. Our universe might be one of many simulated realities, nested within other simulated realities like a hall of mirrors extending to infinity. This idea raises profound questions about the nature of reality and the meaning of existence. If we are simulations, does our experience matter? Are our joys and sorrows real, or mere shadows of something more fundamental? These questions echo ancient philosophical debates about appearance and reality, updated for the digital age. Let us also consider the possibility that different realities might have different arrow of time. In our universe, time has a definite direction, flowing from past to future. Eggs break but do not unbreak. Coffee cools but does not spontaneously heat up. This directionality is one of the most fundamental features of our experience, yet physics has difficulty explaining it. The laws of physics, at the most basic level, are symmetric in time. They do not prefer forward to backward, past to future. The arrow of time seems to emerge from initial conditions, from the particular way the universe began, rather than from the laws themselves. If different universes begin with different initial conditions, they might have different arrows of time. Some might run backward from our perspective, with entropy decreasing rather than increasing. Others might have no arrow at all, existing in a kind of temporal chaos where past and future are indistinguishable. What would it mean for a backward-running universe to intersect with ours? Could we receive signals from the future rather than the past? Could causation run in reverse, with effects preceding causes? These questions verge on paradox, and we do not know how to resolve them. But they illustrate the strange possibilities that arise when we take the idea of other realities seriously. As we continue our exploration of intersecting realities, let us examine the phenomenon of quantum tunneling more closely and consider what it might tell us about the connections between different versions of existence. We touched on tunneling earlier, but this remarkable process deserves deeper attention, for it represents one of the clearest demonstrations that the quantum world does not obey the rules we might expect. In the everyday world, if you throw a ball at a solid wall, the ball will bounce back. It lacks the energy to penetrate the barrier, so it simply reflects. This is common sense, grounded in millions of years of evolution that taught our ancestors to respect physical obstacles. But quantum particles do not always respect these boundaries. An electron approaching a barrier that it classically cannot penetrate will sometimes appear on the other side, as if the wall simply did not exist. The standard explanation involves the wave function of the particle spreading through the barrier. The wave function does not suddenly stop at the edge of the barrier, but extends into it, decaying exponentially as it goes. If the barrier is thin enough, some of the wave function emerges on the other side, representing a non-zero probability of finding the particle there. When we measure the particle's position, we sometimes find it has tunneled through, but consider this phenomenon from the many interacting worlds perspective. In this view, there is no wave function spreading through space. Instead, there are many parallel worlds, each containing a particle at a slightly different position. These worlds interact with each other, pushing and pulling through quantum forces that arise from their proximity in configuration space. When a particle appears to tunnel through a barrier, what might actually be happening is a kind of exchange between worlds. Particles in different realities, each approaching the barrier from slightly different positions, exert influences on each other that can push some of them through. The tunneling particle is not borrowing energy from the vacuum, but from its counterparts in neighboring realities. This interpretation makes different predictions than standard quantum mechanics under certain conditions. If experiments could be designed to detect these differences, we might be able to determine whether tunneling involves interaction with other worlds. Such experiments would need to achieve unprecedented precision, but the potential payoff, direct evidence for the existence of parallel realities, would be worth the effort. Let us turn now to the concept of quantum superposition at larger scales and what it might reveal about the boundaries of reality. We have discussed how individual particles can exist in superposition, occupying multiple states simultaneously until measured. But what about larger objects? Can a cat be in superposition, alive and dead at the same time, as Schrödinger famously suggested? For macroscopic objects, decoherence normally prevents any observable superposition. The interactions with the environment are so rapid and so numerous that any quantum coherence is instantly destroyed. But physicists have been pushing the boundaries, creating larger and larger objects in quantum superposition. In recent experiments, molecules containing thousands of atoms have been placed in superposition states, passing through two slits simultaneously, like the photons in the classic double-slit experiment. These experiments demonstrate that there is no hard boundary between the quantum and classical worlds. The rules of quantum mechanics apply to everything. It is only the practical difficulty of isolating large objects from their environments that prevents us from seeing quantum effects in everyday life. What would happen if we could maintain quantum superposition for truly large objects, like cats or people or planets? In the many worlds picture, such objects would exist in multiple branches simultaneously, with different versions experiencing different outcomes. The branches would only become distinct when decoherence set in, separating the different possibilities into non-interfering realities. Some physicists have speculated that highly isolated systems might maintain coherence for extended periods, allowing quantum effects to influence macroscopic processes. The interiors of neutron stars, for example, are extremely cold and dense, potentially allowing quantum phenomena to occur on scales much larger than in ordinary matter. Could quantum superposition play a role in exotic astrophysical objects? Could there be natural systems where the boundaries between branches of reality remain fuzzy and undefined? These are open questions, and we do not know the answers. But they illustrate how thinking about other realities can inspire new scientific investigations. The multiverse is not just a philosophical curiosity, but a source of potentially testable ideas. Let us consider the role of symmetry in physics and how it relates to the structure of the multiverse. Symmetry is one of the most powerful concepts in theoretical physics. The laws of nature exhibit various symmetries, patterns of invariance under certain transformations. The laws are the same everywhere in space, which is translation symmetry. They are the same in all directions, which is rotation symmetry. They are the same at all times, which is time translation symmetry. These symmetries are not just aesthetic preferences, but have deep physical consequences. According to a theorem proved by mathematician Emmy Noether, every continuous symmetry corresponds to a conserved quantity. Translation symmetry gives rise to conservation of momentum. Rotation symmetry gives rise to conservation of angular momentum. Time, translation symmetry gives rise to conservation of energy. In the multiverse, different realities might have different symmetries. Some might have more symmetries than our universe, making their physics simpler and more elegant. Others might have fewer symmetries, with physical laws that vary from place to place or time to time. The particular symmetries of our universe determine the structure of matter and energy, the forces that bind atoms together, the ways that particles interact. One of the deep questions in physics is why our universe has the symmetries it does. Why is space three-dimensional? Why are there three generations of quarks and leptons? Why does the gauge symmetry of the standard model take the particular form that it does? In a multiverse context, these questions might have anthropic answers. Perhaps only universes with certain symmetries can produce complex structures and observers. Or perhaps there is a deeper reason, a principle of mathematical consistency that selects certain symmetries over others. Let us also explore the concept of quantum coherence in biological systems and what it might tell us about the relationship between life and the multiverse. In recent years, experiments have suggested that quantum effects might play a role in certain biological processes. Photosynthesis, for example, seems to involve quantum coherence, with energy moving through plant cells in a way that exploits quantum superposition for maximum efficiency. If quantum coherence is important for life, then living organisms might be more closely connected to the quantum multiverse than we previously thought. The quantum processes in our cells, in our neurons, in the molecules that make up our bodies, might all be participating in the branching of reality at the most fundamental level. We are not just observers of the quantum world, but active participants, our very existence intertwined with the structure of the multiverse. This connection raises intriguing questions about the nature of consciousness and experience. If quantum processes in the brain involve superposition and branching, does that mean our minds exist in multiple branches simultaneously, at least for brief moments before decoherence sets in? Could the feeling of making a choice, of selecting one option over another, be related to the branching of reality into different outcomes? These questions are highly speculative and controversial. Many neuroscientists doubt that quantum effects play any significant role in brain function, arguing that the brain is too warm and wet for quantum coherence to persist. Others believe that quantum mechanics is essential for understanding consciousness, though they disagree about the details. The debate is ongoing, and the answers remain elusive. Let us now consider the aesthetic dimension of the multiverse and what it reveals about the nature of mathematical truth. Physics has long been guided by a sense of mathematical beauty, with physicists preferring theories that are elegant, symmetric, and economical. Einstein famously said that the most incomprehensible thing about the universe is that it is comprehensible, that the laws of nature can be expressed in beautiful mathematical form. The multiverse challenges this aesthetic sense in interesting ways. On one hand, the mathematical frameworks that lead to the multiverse, like string theory and eternal inflation, are extraordinarily elegant and powerful. They unify diverse phenomena, reveal unexpected connections, and extend our understanding into realms far beyond direct observation. On the other hand, the multiverse itself seems uneconomical, positing an infinite number of realities to explain the properties of just one. Is the multiverse beautiful or ugly, elegant or wasteful? These questions touch on deep issues in the philosophy of mathematics and science. Some physicists embrace the multiverse as the ultimate expression of mathematical possibility, a structure so rich and complete that it contains everything that could exist. Others reject it as a betrayal of scientific economy, a retreat from the search for unique explanations. The debate reveals something important about the relationship between physics and aesthetics. Our sense of beauty has been shaped by evolution and experience, tuned to patterns that help us survive and thrive in our particular environment. There is no guarantee that this sense will be a reliable guide to the fundamental structure of reality. The universe might be beautiful in ways we cannot appreciate, or ugly in ways we refuse to accept. Let us consider the idea of the mathematical universe hypothesis, proposed by physicist Max Tegmark. According to this hypothesis, every mathematical structure exists as a physical reality somewhere in the multiverse. Our universe is not special, but simply one mathematical structure among infinitely many, realized as a physical cosmos with its particular properties and laws. This is perhaps the most extreme version of the multiverse concept. It implies that there is no distinction between mathematical existence and physical existence. If something can be described mathematically, it is real. The multiverse contains not just variations on our physics, but entirely different mathematical worlds, with different logics, different numbers, different geometries. The mathematical universe hypothesis is difficult to test and perhaps impossible to prove. But it has a certain logical completeness that some find appealing. If the multiverse exists, why should it contain only certain mathematical structures and not others? What would select some possibilities for realization while excluding others? The principle of plenitude, the idea that all possibilities are realized, seems to follow naturally from the multiverse concept. Let us now bring our attention back to the intimate scale, to our lives and experiences as conscious beings contemplating the cosmos. We have traveled far in this exploration, from quantum particles to cosmic horizons, from mathematical abstractions to philosophical paradoxes. It is easy to feel lost in the immensity, overwhelmed by the scale and strangeness of the ideas we have encountered. But there is comfort to be found in this vastness. The universe, for all its apparent indifference, has produced us. Out of hydrogen and helium, through billions of years of stellar evolution and chemical complexity, conscious beings have emerged who can look up at the stars and wonder. This is not an accident or a coincidence, but a natural expression of the universe's creative potential. If other realities exist, if there are countless versions of the cosmos spreading through the quantum tree and bubbling in the inflationary void, then this creative potential is even greater than we imagined. Every story that could be told is being told somewhere. Every form of beauty that could exist does exist. Every possibility is explored, every path is taken, every dream is dreamt. This is not a diminishment of our significance, but an amplification. We are part of something magnificent, something that stretches beyond the boundaries of space and time, into realms we can barely conceive. Our particular branch of reality, our particular sequence of experiences, is precious precisely because it is ours. No other version of you is living your life. No other branch contains the exact combination of choices, relationships, and moments that define your existence. The multiverse, if it is real, does not make us smaller. It makes us larger, connecting us to an infinite community of possibilities. It invites us to see our lives not as isolated events in a cold and empty universe, but as threads in a vast tapestry of existence, woven together with countless other threads into a pattern of incomprehensible beauty. As we approach the final stages of our journey, let us return once more to the scientific foundations and consider what the coming years might bring. The search for evidence of other realities is ongoing, and new discoveries could come at any time. Each observation of the cosmic microwave background, each detection of gravitational waves, each experiment at a particle collider, brings us closer to understanding the true structure of the cosmos. The most likely scenario is that the evidence will remain ambiguous for the foreseeable future. The anomalies in the cosmic microwave background might turn out to have mundane explanations. The searches for extra dimensions at the Large Hadron Collider might continue to come up empty. The predictions of different multiverse theories might remain too imprecise to test definitively. But science has surprised us before. Discoveries often come from unexpected directions, revealing phenomena that no one predicted. The multiverse might make itself known through some observation we have not yet imagined, some signal from beyond the boundaries of our reality that cannot be explained any other way. Or the multiverse might remain forever hidden, a logical possibility that nature chose not to realize. We might be alone after all, a single universe in a vast emptiness, unique and precious and utterly isolated. This would not diminish the wonder of our existence. If anything, it would make our cosmos even more remarkable, a lone oasis of structure and complexity in an infinite desert of nothing. Either way, the search continues. The human spirit is not content with mystery, but is driven to understand, to probe, to question. We will keep building telescopes and particle accelerators. We will keep developing theories and testing predictions. We will keep looking up at the stars and wondering what lies beyond. Let us take a moment to appreciate the remarkable fact that we can even contemplate these questions. The universe has produced beings capable of understanding themselves, of constructing mathematical models of their own existence, of imagining possibilities beyond the reach of direct observation. This is perhaps the greatest mystery of all, greater than quantum mechanics or cosmology or the multiverse. How did matter come to know itself? How did the universe learn to ask questions? There are no easy answers, but the questions themselves are precious. They connect us to generations of thinkers who came before, who looked up at the same stars and wondered the same things. They connect us to future generations who will carry the torch of inquiry forward, discovering things we cannot imagine. We are links in a chain of consciousness that stretches back to the first human who gazed at the night sky in wonder and forward to whatever our descendants might become. The idea of other realities is part of this grand tradition of questioning. It represents our latest attempt to understand the cosmos, to push beyond the boundaries of the known into the territories of the possible. Whether the multiverse is real or not, the act of contemplating it expands our minds and enriches our experience. We become larger by entertaining large ideas, even if those ideas turn out to be wrong. Let us explore the concept of cosmic memory and whether information from other realities might somehow be preserved across dimensional boundaries. In our universe, information is conserved. The laws of physics, at their most fundamental level, are reversible. In principle, if we knew the complete quantum state of the universe at any moment, we could calculate its state at any other moment, past or future. This conservation of information raises intriguing questions in the multiverse context. If information is conserved within each branch or bubble, is there any way for information to flow between different realities? Could the information content of our universe bear traces of interactions with other universes, echoes of cosmic events that occurred in different dimensions? We have already discussed how gravitational waves might leak between branes and how collisions between bubble universes might leave marks on the cosmic microwave background. These would be examples of information transfer between realities, but there might be subtler forms of cross-reality communication involving quantum correlations or topological connections, or something else we have not yet conceived. Some physicists have speculated about the possibility of wormholes connecting different branches of the quantum multiverse. In the many worlds picture, branches that split at some point in the past might be rejoined by quantum processes, creating loops in the branching structure. If this were possible, information from one branch might be transmitted to another, with potentially observable consequences. These ideas are highly speculative, and we have no evidence that such connections exist, but they illustrate the creative possibilities that arise when we take the multiverse seriously. The boundaries between realities might be more permeable than we imagine, allowing subtle exchanges that we have not yet learned to detect. Let us consider the possibility that our universe might be young compared to the multiverse as a whole. If eternal inflation has been going on forever, then bubble universes have been forming for an infinite time. Some of these bubbles might be vastly older than ours, having gone through cycles of cosmic evolution we can barely imagine. What happens to a universe as it ages? Does it eventually fade into darkness? Or are there processes that allow cosmic structure to renew itself over time? In our universe, the stars will eventually burn out. The fuel for nuclear fusion is finite, and once it is exhausted, no new stars will form. The cosmos will become a cold, dark place, populated only by black holes, neutron stars, and cooling white dwarfs. Eventually, even these remnants will decay, leaving nothing but a thin soup of elementary particles spreading ever thinner through an ever-expanding void. This fate, known as the heat death of the universe, seems bleak from our perspective, but in the context of the multiverse, it might be just one chapter in an infinite story. Other bubble universes might have different fates depending on their physical constants and initial conditions. Some might collapse in a big crunch. Others might tear themselves apart in a big rip. Still others might experience phenomena we cannot even imagine, transitions to new phases of existence with different properties and possibilities. The multiverse, viewed as a whole, would encompass all these different outcomes. It would contain universes at every stage of evolution, from the hot, dense aftermath of the Big Bang to the cold, empty expanse of heat death. It would be eternal, not just in the sense of lasting forever, but in the sense of containing every moment of cosmic history simultaneously, spread across an infinite landscape of possibilities. Let us also consider the relationship between the multiverse and the concept of eternity. Our human experience of time is linear and finite. We are born, we live, we die. Our lives are bounded by beginning and end, stretching for a few decades in a cosmos that has existed for billions of years and will continue for billions more. Against this backdrop of cosmic time, our individual existences seem vanishingly brief. But in the multiverse, time takes on new dimensions. Different branches of the quantum tree represent different moments in cosmic history. all existing together in the timeless wave function. Different bubble universes have their own independent timelines, stretching from their particular Big Bangs into their particular futures. The multiverse does not flow through time like a river, but contains all of time within itself, like a vast ocean that holds every wave that has ever risen or ever will. This perspective can change how we think about our own mortality. In a single universe, death seems like an absolute ending, a passage into non-existence from which there is no return. But in the multiverse, every moment of our lives persists in some branch of the cosmic tree. The Phage version of you reading these words exists eternally in the wave function, as do all the versions of you that came before and all those yet to come. Nothing is ever truly lost, because everything that has happened continues to exist in the structure of reality itself. This is not immortality in the conventional sense. We still experience time linearly, and our individual threads of consciousness still have beginnings and ends. But it is a kind of permanence, an assurance that our existence leaves an indelible mark on the fabric of the cosmos. The multiverse remembers, even if we forget. Let us return now to the practical implications of these ideas and consider what they might mean for the future of human civilization. If other realities exist and we can learn to detect them or interact with them, the consequences would be profound. We would no longer be alone in the deepest possible sense. We would have neighbors, even if we could never visit them. This knowledge alone could transform our perspective on our place in the cosmos. Throughout human history, we have gradually learned that we are not at the center of things. The Earth orbits the Sun, not the other way around. The Sun is one of billions of stars in the Milky Way. The Milky Way is one of billions of galaxies in the observable universe. Each step has displaced us further from any central position, but each has also revealed a cosmos more vast and wonderful than we knew. The discovery of other realities would be the ultimate step in this progression. It would show that our entire universe, vast as it is just one among many. Our laws of physics, our particular configuration of matter and energy, would be one possibility among countless others. We would be cosmically ordinary and cosmically connected, part of a structure of existence that exceeds our previous imaginings by an infinite factor. Some might find this diminishing, a blow to human significance, but another perspective sees it as liberating. We would no longer bear the burden of being the only reality, the single fragile exception to the rule of emptiness. We would be part of a community of existence, even if that community is spread across dimensions and barriers we cannot cross. As we bring our journey to a close, let us gather the threads of what we have explored and weave them into a final tapestry. We began with a question. What if another reality has been intersecting, ours since the beginning of time? We have followed this question through the strange landscapes of quantum mechanics, where particles exist in multiple states at once, and the act of observation shapes reality. We have ventured into the realms of string theory and extra dimensions, where our universe might be a membrane floating in a higher dimensional space. We have contemplated the infinite bubbles of eternal inflation and the cosmic collisions that might leave their marks on the sky. We have considered the philosophical implications of these ideas, the questions they raise about identity, free will, consciousness, and meaning. We have allowed ourselves to wonder about the nature of existence itself, about what it means to be real in a cosmos that might contain everything that is mathematically possible. And now, as the stars wheel overhead and the universe continues its ancient expansion, we arrive at a moment of peaceful contemplation. The questions we have explored may never be fully answered. The multiverse may remain forever beyond our reach, a logical possibility that we cannot confirm or refute. But the exploration itself has value. It has stretched our minds, expanded our imaginations, and connected us to the deepest mysteries of existence. The night is quiet now. The universe hums with the subtle energies of the cosmic microwave background, the echo of the Big Bang still reverberating through space after billions of years. Somewhere, perhaps, other versions of this moment are playing out in other branches of reality. Other conscious beings, in other bubbles or on other branes, might be looking up at their own skies, asking their own questions, wondering about the nature of the cosmos they inhabit. We are all part of the same great story, even if we can never meet. We are all expressions of the universe's capacity to know itself, to question, to wonder, to seek. This is our gift and our responsibility, to carry forward the flame of inquiry, to keep asking questions even when the answers lie beyond our grasp. The cosmos is vast beyond measure, and it may be vaster still. Other realities may be touching ours at this very moment, invisible and intangible, yet cosmically close. We cannot know for certain, but we can wonder. And in that wondering, we participate in the greatest adventure of all, the journey of consciousness through the landscape of existence, seeking understanding in a universe that rewards curiosity with endless mysteries. Let this peaceful contemplation stay with you as you drift towards sleep. The cosmos holds you, cradles you, surrounds you with its ancient light. You are part of something magnificent, something that stretches beyond the boundaries of what we can see and touch. Whether we are one reality among many or the only reality that is, we are precious, we are remarkable, we are home. And so we come to the end of our exploration, but not the end of the story. The story continues in laboratories and observatories around the world, where scientists work to unlock the secrets of the cosmos. It continues in the minds of thinkers and dreamers who contemplate the nature of existence and imagine possibilities yet to be conceived. It continues in you, the listener, who has journeyed with us through these ideas and now carries them forward into your own life. The multiverse, if it exists, is vast beyond comprehension, but it is made up of moments, of choices, of experiences. It is made up of lives like yours, each one a unique thread in an infinite tapestry. Your existence matters, not despite the vastness, but because of it. You are a point of light in the cosmic darkness, a center of awareness in a universe that might otherwise be unconscious. Rest now, and let these thoughts settle into your mind like stars settling into the evening sky. The universe will be here when you wake, still expanding, still evolving, still keeping its secrets while slowly revealing them to those patient enough to look. And perhaps, in dreams, you will catch a glimpse of other realities, other possibilities, other stories being told in the endless library of the multiverse. Thank you for joining us on this journey through the cosmos. Sleep well and dream of stars. As a final meditation before we part ways, let us consider the profound silence of the cosmos and what it might be telling us. When we turn our radio telescopes to the sky, listening for signals from other civilizations, we hear nothing but the hiss of static and the natural radio emissions of stars and galaxies. This silence has puzzled scientists for decades. If the universe is so vast, so old, so full of stars and planets, where is everyone? Why do we not detect signs of advanced civilizations spreading through the galaxy? The multiverse offers an interesting perspective on this puzzle. If there are infinitely many realities, then intelligent life exists somewhere in almost every configuration imaginable. There are universes where life is abundant and universes where it is rare. There are universes where civilizations reach out to each other across the stars, and universes where they remain forever isolated on their home worlds. In our particular branch of reality, we might simply be in a quiet corner, a region where the nearest civilizations are too far away or too unlike us to make contact. Or we might be among the first, emerging in a universe still young by cosmic standards, with most intelligent life yet to evolve. The silence we hear might not be absence but timing, a consequence of where and when we happen to arise. But there is another possibility, one that the multiverse makes more poignant. Perhaps we are rare not just in space but across the landscape of realities. Perhaps the conditions that give rise to conscious beings like us are so specific, so dependent on a precise combination of factors, that even in an infinite multiverse we are exceptional. This would not make us unique, for in an infinite multiverse there are no unique things, but it would make us precious, a form of existence that arises only under special circumstances. The search for extraterrestrial intelligence continues, with new telescopes and new techniques constantly improving our ability to detect signals from other worlds. If we ever succeed, if we ever hear a message from beyond our planet, it will be the most significant discovery in human history. It will show that the universe produces consciousness, not just once, but repeatedly, that the miracle of awareness is not confined to one small world orbiting one ordinary star. But even if we never find anyone else, even if the silence continues forever, we will still have each other. We will still have the community of human beings, past and present and future, all asking the same questions and seeking the same understanding. This community is itself a kind of multiverse in miniature. Countless individual perspectives on reality, countless unique experiences of existence, all interconnected through language and culture and shared humanity. The cosmos has given us the gift of consciousness, the ability to wonder and to question and to seek. This gift comes with no guarantees, no promises of answers or companions. But it is enough. It is more than enough. It is everything. Think of all the people throughout history who have looked up at the night sky and felt the same sense of wonder you feel now. Think of the ancient astronomers who mapped the stars without telescopes, the medieval scholars who preserved knowledge through dark ages, the Renaissance thinkers who first glimpsed the true scale of the cosmos. Think of the modern scientists who have revealed the secrets of atoms and galaxies, quantum mechanics and relativity, inflation and dark energy. You are part of this lineage, this unbroken chain of curiosity reaching back thousands of years. And think of the future, the generations yet to come, who will inherit our knowledge and carry it forward. They will discover things we cannot imagine, answer questions we do not know how to ask. They might confirm the existence of other realities or rule it out forever. They might make contact with other civilizations or confirm our cosmic solitude. Whatever they find, they will be continuing the work we have begun, the endless human project of understanding. This project gives meaning to our existence in a way that transcends the cold equations of physics. Yes, we are made of atoms forged in stars. Yes, we emerge through billions of years of evolution on a small planet in an ordinary galaxy. Yes, we will eventually return to the cosmic dust from which we came. But in the meantime, we are the universe knowing itself, the cosmos becoming conscious of its own nature. This is not a small thing. This is the most remarkable thing that has ever happened. The multiverse, if it exists, makes this achievement even more significant. It means that consciousness has arisen not just once but countless times, in countless variations, across an infinite landscape of possibility. It means that the universe is not just vast, but alive with awareness, filled with beings who think and feel and wonder. We are not alone in the deepest sense, even if we are alone in our particular bubble or branch. Let this thought bring you peace as the night deepens. The stars are watching over you, ancient and patient, burning with the same nuclear fires that forge the atoms in your body. You are stardust contemplating the stars, a temporary arrangement of matter that has learned to ask questions about itself. This is not meaningless. This is meaning itself, the highest purpose the universe has yet discovered. And somewhere, perhaps, in another branch of reality, or another bubble universe, or another brane floating in the bulk, another version of this moment is unfolding. Another conscious being is looking up at different stars, feeling the same wonder, asking the same questions. You are connected to them across barriers you cannot cross, through bonds you cannot perceive, in ways that mathematics can describe but words can only gesture toward. Sleep now, and let the cosmos hold you. The mysteries will still be here tomorrow, patient and eternal, waiting for the next generation of questioners to take up the search. You have done your part tonight, opening your mind to possibilities that stretch beyond the horizon of the known. Rest well, dreamer of infinite dreams. The universe whispers its secrets to those who listen. Keep listening, keep wondering, keep asking questions that have no easy answers. This is what it means to be human. This is what it means to be alive. This is what it means to be part of the greatest story ever told, the story of existence discovering itself, one curious mind at a time. Good night, traveler. The stars will guide you home.